times, let's see, 0 take away 5. Negative 5. And then 0 add 1. 1. And then what about the rest of them?
0.
They're all gone. Does everyone see how these two are gone? I'm not going to write them down, but they're gone, right? And that means that A is what? Negative 1/5, right? All you'd have to do is say this is negative 5A, and then divide both sides by negative 5. We can get B the same way, can't we? Hopefully. In order to get B, what I'm doing is I'm really just looking for the factor that appears in both of these that does not appear in this one, which would be the factor x minus 5, right? And in order to make x minus 5 become 0, I'm going to have to let x be 5. If I do that, then I'm going to get 1 equals, so I'm back into here, 1 equals, this goes away, right? That goes away because I'm putting a 5 right there. That's 0. Who cares what everything else is? That's gone. Also, this one's gone. Gone. But I have to put a 5 here and a 5 here. So 5 and then 6. 5 times 6 is 30. So 30b. So b is 1 over 30. I told you there would be fractions, right? I told you. All right, finally, let's get c. To get c, we let x be, drum roll, negative 1, right? Because the c term is missing the x plus 1 factor. So to make x plus 1 become 0, we let x be negative 1. And then that equation turns into 1 equals, let's see, this is gone, this is gone, negative 1 here, negative 1 there. So negative 1, this is negative 1 take away 5 is negative 6. Negative 1 times negative 6, 6. 6c? Okay, c is 1/6. Bam, we're there. We're there. I can now do this integral. I want to finish the problem, so let's finish it. So to finish this, that integral now turns into the integral of, let's see, it was a over x, right? A over x. A over x. And a for us was? Negative 1/5. Watch the way I write this. Negative 1/5 over x. Just leave it like that. I know it looks weird. Just do it. Plus, now b was 1 over 30? 1 over 30 over x minus 5. And then plus c, which was 1 over 6 over x plus 1. All of that, right? We broke it up. Partial fraction decomposition. Now, this is the same as negative 1/5 integral 1 over x dx plus 1 over 30 integral 1 over x minus 5 dx plus 1/6 integral 1 over x plus 1 dx. See these constants? You can just pull them out of the integrals. Just pop them out. Pop it out, pop it out. And then just each one of those should be straightforward, right? Because each of these is just constant over linear, constant over linear, constant over linear. Final answer, negative 1/5. What? Natural log absolute value x. Plus 1 over 30, natural log absolute value x minus 5. Right? Each of these are just, well, this one's just the formula, but aren't these just basic U subs? Because this is linear down here, so basic U sub. We started class with that last time. And then plus 1/6 natural log x plus 1 plus a constant. We're done. So far, how do y'all feel about it? I mean, some of y'all said y'all didn't, like y'all hadn't had partial fractions, right? You hadn't seen it yet. So far, is it okay? Okay, it's going to get a little worse because right now we're sticking to distinct linear factors, right? Everything has been distinct linear factors. The question will become, what if we have repeated linear factors down here? Like, what if we have x times x minus 5 squared, then x plus 1? Or what if what's down here is not linear but quadratic but can't be factored? Something like that. So we got to kind of extend this, and we'll do that next class. But let's tackle the first problem up there, because this one's going to work out real nice. Okay, x cubed plus x over x minus 1. When it comes to the steps for finding the antiderivatives of rational functions, when it comes to steps, I haven't given you any steps, have I? I haven't given you any steps on how to do this. I'm just kind of showing you how partial fraction decomposition works. I want you to look at that. And do y'all see that we only have on the bottom one distinct linear factor, right? So there's no partial fractions that you can do here because you only have one thing on the bottom, one distinct linear factor. But more importantly, let's make sure we can't do this using any other method. You could factor an x out of the top. Let's see, if we did that, what would it look like? X squared plus 1? So that algebraically is fine, but does that help you at all in terms of being able to do it, right? So let's see, what do we have? Integration by parts. I don't see that. I don't see anything helping there. Trig sub. Maybe with the x squared plus 1. Maybe you could do a trig sub here, maybe. But overall, isn't this a rational function? It's a polynomial over a polynomial, right? So if it's a rational function, we want to follow the procedure for rational functions, which I haven't given you, right? So the procedure is this, and I have it in the notes, and I'll put it up next time. I'm just going to tell you right now. The first step when you're trying to integrate a rational function, the very first step is to compare the degree of the numerator and denominator. Okay, so degree is the highest power of the polynomial. So what is the degree of the numerator? 3. What's the degree of the denominator? 1. You compare those. If the degree of the top is bigger than or equal to the bottom, you have to do a step first before you try and do anything else. All right? If the top power is bigger than or equal to the bottom, you have to do something first. You ready to know what it is? Long division. You have to do long division first. That's your first step. All right? So is 3 bigger than 1? Yes. And since 3 is bigger than 1, the very first step of rational function integration, which again I'll show you later, is long division. Let me show you the steps, just so you can see what I'm talking about. The strategy right here. Here's the strategy for integrating rational functions. Inspect the degree of the numerator and denominator. Okay, take a look at the degree of the degree of numerator and denominator. If the degree of the numerator is less than the degree of the denominator, then you move on. But if the degree of the numerator is greater than or equal to the degree of the denominator, we must first do long division. So our very first step is going to be long division, which every time I say, it has been 100% of the time my entire career, when I have mentioned long division, it is followed by sighs and, just like reaction. There's never been like, hell yeah, long division, let's do it. There's never excitement when I mention long division. You like? Okay, thank you. Well, the initial reaction that I get is never that. Right. Thank you. So how do we do long division? We take what's in the numerator, we put it in the division box. We take what's in the denominator, we put it on the outside. You must put everything in descending order, highest power down. And anytime you have a missing power, you have to put a space. So, okay, what do I mean? X cubed plus 0x squared plus x. That's the numerator written including an x squared position because while I do division, I need to make sure that if I ever get an x squared, I have a place for it. On the outside, I put the x minus 1. And now we play a game where we look at the power, you look at the x here, and you look at this x cubed there, and you say, what do you multiply x by to get this? X squared. And you put that up here, right? It doesn't matter where you put it. A lot of times students are taught to put it above the x squared. It doesn't matter where it goes. I'll put it here, though, anyway. So x squared. Now, I take that x squared, and I distribute it to each one of these terms. So what's x squared times x? X cubed. What's x squared times minus 1? Negative x squared. I put that right here underneath the x squared. Line it up. And then you subtract that, right? Then you subtract that. Why do we subtract? But why subtract? Why not add? Yeah, but why subtract? I mean, you just told that, right? You're just told that's what you do, right? Just like this, like back in the day, if you do 15 divided by 4 back in grade school, you go like that. You go, 4 goes into 15 how many times without going over? 3. Then you what? 3 times 4 is 12, and then you subtract. We're doing the exact same thing here, all right? Subtract, you get 3, and then here, 4 doesn't go into 3, so that's your remainder, right? And back in the good old days, we put R3, right? That was fun. But like, it's the same method, right? It's the same method. So we have this. Now we subtract this row. We have to remember to subtract the row. Subtracting the row really has the effect of changing the signs, right? Everything that was negative becomes positive. Everything that's positive is now negative. Okay, now you add down. So those go away, right? What do we have here? X squared plus x. And now you play the game again, but now what you're doing is you're looking at the x here, and you're saying, what does it take to turn it into x squared? Plus x. Put that here. And then you do the same thing. You do x times x, and then x times negative 1, and you put those things under here. So x times x, x squared. And x times negative 1, negative x, right? Put it right there underneath that x. Then I come through and subtract, right? Which changes this to minus and this minus to plus. See, those x's at the end don't go away, right? These go away. This is 2x. Okay. Try and do it again. What do you multiply x by to get 2x? 2. So I put a 2 here. And now multiply 2 times x, and you get 2x. And then 2 times negative 1, you get negative 2. Put it out here. Come through and subtract again. And when you add down this time, what do you get? 2. And now we play the game again. What do you multiply x by to get 2? Well, you can't now, right? You're kind of at the point that you were here. That doesn't make sense. You're at the point that we were here where 4 doesn't go into 3. You can't turn 4 into 3. So it's like the same thing. You can't turn x into 2. You can, but it would require a fraction. So we stop, and that's our remainder, right? That's our remainder. So what we write next to this is not R2, right? We don't do that, right? We don't do that. What we do is this. We write plus the remainder over the divisor. The remainder over the divisor. See, back in grade school, when you did this, you were taught to write what? 3 3/4? Do you all remember being taught to do that? 3, and then whatever this is over this, put it next to it. And this is called, do y'all know what this is called? A number written this way? A mixed number, right? Mixed numbers suck, all right? Mixed numbers suck because people don't know what they are. A lot of people don't know what they are. This is really 3 plus 3/4. That's what that really means. 3 3/4 really means 3 plus 3/4. The notation sucks because it could be misinterpreted as multiplication. You could think that that's really 9/4, which it's not. So Like yeah, I wish we just never used those. But anyways, that's what it really means, okay? So that's exactly what I'm writing here. I'm saying, okay, it's this, and then whatever the remainder is over the divisor, I'm adding that to it. And so now this integral becomes what? Instead of this, I can write all that, can't I? X squared plus x plus 2 plus 2 over x minus 1 dx. How do you feel about integrating that? A lot better. You should feel good about that, right? Because there's a bunch of additions there. Subtraction? No, just additions, right? Can you integrate that? 1/3 x cubed. Can you integrate that? 1/2 x squared. Can you integrate that? Sure, 2x, right? Power rule, power rule. Okay, can you integrate that? 2 natural log, absolute value x minus 1 plus c. Boom, we're done. So integrating rational functions, the very first step is long division, right? Now, in this particular example I gave you, we did long division, and then once we saw what we were left with, we actually could handle it, right? So we were done. Where we're headed next class is that we're going to have to do long division first, and then this new answer we get, yes, some of it we'll be able to handle, but then one of these pieces is going to look like the problem we did before this one, where we have to do partial fraction decomposition on that one piece. And so, yeah, that's where we're going. We don't have enough time to start a new problem. So what do I want you to do for homework? I don't even know. We're not done with this section. Why don't you try, yeah, let's look at those two. Looking at these rational functions here, you can take a picture of this before you leave. What I'd like for you to do is on the G, see if you can do partial fraction decomposition on that. So on G, the degree up here is smaller than here, so you don't have to do long division first. But you should be able to factor this, and then you should have distinct linear factors, and then do what we did, all right? And then this one you can't do because it has a greater power. So if you want, why don't you try long division on this one? Okay, so do partial fraction decomposition on this, see if you can split it up. And on this one, try long division. And then on this one, try long division. All right, that one when we come to class, you've at least tried that part. I'll go through it, but so everyone clear? Ignore J completely, all right? This one, try partial fraction decomposition. This one, just do what? Long division. This one, long division, okay? And this is probably the last day. Next class when we meet, after that, pretty much you have all the homework assignment to look at. Right now, we haven't done enough to throw you into it yet. So this would be a good opportunity this weekend to get caught up, review some things, you know. All right, everyone. I think I'm done. I want you to do that for homework or just get caught up.